Hi there, welcome to this session on bootstrapping UVM based verification with the UART Testbench. Typically our bootstrapping sessions are wherein we go take a real life example and look at how to apply UVM to that particular real life example. We have been doing this, so we have done like bootstrapping with Verilog, wherein we tried applying verification process with a Verilog on a counter example, and then we did bootstrapping system Verilog based verification, wherein we applied the overall verification process with the FIFO test bench. And so this is the third part in the series wherein we are doing bootstrapping UVM based verification, and in this session we'll be applying how to build UVM test benches for the UART duty. And what I would like to iterate over here are two things. First is like after going through the session on UVM core concepts, both the part 1 and part 2, you would have gotten some idea, but I understand that it may not all be clear, like when we said like let's say for example raise objection and drop objection to hold the test in the run phase, or when we talked about phasing, or when we talked about extending base classes, all those still remained at a very theoretical level or at a definition level, and some of those concepts might not have become very clear in your mind. Okay, so in this session what you will be able to see is you will be able to see them in action, so it will definitely give you further level of clarity as to when we say extend a base class, what exactly do we mean, when we say phasing, real what happens during each of those phases, and we will look at the real life code snippets, and we will understand that to a next level of depth. And the second thing that we have been emphasizing throughout this course is learning patterns. Okay, so this is opportunity to make sure that you learn one pattern of how to apply UVM to solve a verification problem. Okay, so this is the second this is the second reason why we do the bootstrapping, that you get to know at least one pattern. And what you should do is during this session as well as after this session, you should be again looking at the code by yourself. Okay, and try to understand that what you have learned over here, when you look at the code, are you able to apply that, and are you able to convince yourself of your understanding, right? So that is another important part. And then pick the components from the test bench, take them apart, do their individual simulation. If you find that entire test bench simulation looks daunting, then you can take individual parts and do the simulation in parts as well, to understand each one of them better. So those are the things that if you do, then you will get much better hold on these concepts. And the last thing that I would like to say is that don't think that we will stop at only one pattern. One pattern minimum you should know, but for each of these concepts the subsequent to this bootstrapping will go much deeper. Take a, like for example, config DB and understand how the config DB works. We'll take a phasing, go in detail how phasing works. We'll take, for example, sequence, sequencer and driver interaction and go deep. So there we will not worry about the UART test bench much, but we will look at different possible ways in which things can be done. But in UART test bench, we will show you one of the ways. And the expectation is that at least you remember one of the ways more thoroughly and more perfectly. If you are not able to remember all possible ways of using UVM, that might be fine initially, but you should remember one of the ways. That is the key. And other thing is that as soon as you finish this session, our goal has been that you should be ready every day. Okay, so as soon as you finish this session, you are UVM aware verification engineer, right? So you can look at a given test bench, because as we have been discussing, in most of the time in industry, many of us will not get a chance to build something from the scratch immediately, but many of us will get a chance to take something that exists and do some enhancements, right? That is what is the most likely possibility. In those cases, you should have at least one pattern in your mind that you can use it for questioning, that you should know, okay, what does a sequence mean, what does a monitor mean, what does a driver mean, how they get implemented, right? And the overall thing more or less remains same, right? 60 to 70% of it remains same, only some 30 to 40% is very different. So if you have the pattern in your mind, then you can ask those questions. So if somebody asks you to write a test case, then you can say, hey, okay, sure, I can go and look at what are the sequences available, and I'll understand those sequences and use those sequences to write a test case. So that is the key. It's not about the UART test bench, right? It's about understanding the pattern so that you can translate that pattern to asking the questions about the test bench that you will eventually work on. That is the key over here. That is why we look into code written by somebody else in much more detail to enhance our skill of understanding the code written by others and understand it as one of the patterns. So that is the whole idea of this process. And what you need to do is, at some cases, like for example, we will go one level deeper than compared to core concepts, but still we may not define each and everything. So some of it you might still have to accept it on face value and apply your common sense, since now you already know about verification, right? So you already know about verification, so you should be able to think from the point of view of how the verification process is getting eased or is becoming better with UVM, right? And you should be able to say, hey UVM, show me how are you generating stimulus, how are you doing checks, how are you doing coverage, right? And how are you making my environment more flexible, more reusable, right? Those are the questions now you are already equipped to ask, and you should be asking those questions and then looking at this presentation as an answer. And don't think that you don't know anything about it and then you are trying to learn. Don't think like that. Okay, so you already have the background, connect to that background so that that also becomes stronger, and your experience of learning the concepts of UVM become much more easier if you do that. Okay, so with that background, let's jump into this session. We have the following agenda for this session. So this is in two parts in a way. This is the first part. What we will do is we'll look at a little bit about the DUT. So our goal is not to go very deep into the UART protocol itself. That is a prerequisite for this session. So this UART Testbench uses two protocols. It uses APB protocol and as well as UART protocol. Okay, so for the APB protocol, we will provide you like a full session, because we would be demonstrating how to build APB UVM agent. So in that context, we will also show you the APB protocol, because that's needed to build the agent. Whereas for the UART protocol, understanding is a prerequisite. You don't need to know it in a very high detail, as long as you overall at least understand to the extent that you program something parallel, gets converted to serial and sent out, and you receive something serial, gets converted into parallel and read back by the processor. To that extent it is enough, but it is recommended for your general awareness that you do go through the UART protocol. But it's not that for understanding this session you don't need to know anything beyond parallel to serial and serial to parallel conversion, whereas APB will do a deep dive, because we want to demonstrate how to build a UVM APB agent, which is separate from this session. Okay, so that is the idea. So with that background, the first thing we want to understand like overall UART DUT. Okay, so when we talk about any DUT, right, especially the one that gets into a SOC, that's the one that we are trying to focus, but that's a popular use case. So one that goes into SOC will have three views, right? First view is what is its signal boundary, what are the different signals that it provides that need to be hooked up into your SOC. That's the first thing, right? And second thing is what is the software view, right? How does code that runs on your processor interacts with this IP that we are connecting? That is a software view, right? That is the second thing we need to know. Third thing is if it is a protocol type of a thing, or whatever functionality that it is implementing. Currently we are dealing with the protocol, so what exactly is the protocol that it is implementing? So those are the three things that we need to know. So from UART point of view, we will look at the signals in detail. The key signals we look into in the detail. Second, software view we look into it in detail, because that we need to use while building the test bench. Without the software view we cannot build the test bench. That is important. Third, the protocol view. Unless you really plan to build an agent for that particular interface, then the protocol level view at a detail is not required. Okay, just the abstracted view that oh, I just want to transmit something, or what have I received. To that extent it is sufficient. Okay, so protocol view need not be very detailed unless and until you plan to build an agent. That is the key point, right? So for the UART DUT, we will look at it from an interface view of the DUT, that is what are its signals, how do we connect it, because we need to connect this DUT and pass this signals to our test bench. That's why we will look into it. Second, we'll look into a software view of this DUT, because we need to build the UVM RAL model for it, and then we need to build the sequences which program the DUT to transmit something or to read the data our UART DUT has received. Because ultimately, as I told, all that our UART DUT is doing is it is taking a parallel data, serializing it in some format and sending it out to the other side, and it is receiving a serial data from the other side, creating a parallel data word according to how it has been configured, and it is delivering the data that is received to the test bench or to the software, right? This is what is the, like at a very high level, what is the functionality that the UART is doing. Now on the line, what protocol does it follow, like how does it do the start bit, how does it do the data bit, what does it do with the parity, stop bit, all that we are not going to go very detail in that, right? That is the details that is handled by the agent. So what we are going to do, so we are going to assume that we have bought a UART VIP from some vendor, and we have taken this DUT, we have attached the UART VIP or the UART agent to it, and we have also bought a APB agent, we have attached the APB agent, right? Now that we have bought these two, because that is the primary business case of the UVM that we talked about, right? That is, we can buy various verification components, either buy from a third party vendor, or buy it from an internal team, right? Buy or a borrow, right? Borrow it from an internal team and put it together, and we can reuse and build our test bench on the top of it. So in for this session, the way we are going to do it is, we are going to say, yeah, we have a UART agent, we have a APB agent, we take those two agents and then build our UVM test bench on the top. That is what we are going to do. Okay, but after this session you will have one more session wherein you will build a APB agent. So when you build the APB agent, we will also go into the details of APB protocol. Okay, does that make sense? So that is our overall path. So we will look into the interface level of DUT, we look into the software view of DUT. For the protocol view of DUT, we are going to be borrowing the agent in this particular case. Okay, and then we will look at some of the scenarios to test, because we are primarily focused from verification point of view. So what are the scenarios that we intend to test? Then we'll pick one scenario. Okay, we will pick one scenario which consists of transmitting something, receiving something, both the direction. It consists of doing something on the DUT for both the direction. We'll look at that particular scenario in the simulation log, that how exactly it has done. We'll take that particular command line that we are running, go into the log file, look at what exactly it has done, and then we will correlate that to the waveforms, right? So we'll look into the waveforms and correlate what we have seen in the logs to the waveform. Okay, and that is a point where we have gained a very good understanding of what is it that we want to accomplish. So we are starting backwards, right? So this is what we want to do. We want to create this particular scenario, and how it is going to look in the simulation log file, how it is going to look in the waveform, that is what we are going to establish, and then we will work our way backwards in order to accomplish it, right? That is the idea. So once we have established what we want to see, then we come back and start creating start looking at an existing UART test bench that leads to this particular log and waveform. So we are going to look at a UART test bench. We'll start off with the directory structure. So you will be able to see that when you say reuse, you also need to organize components such that you can reuse. Like for example, we are saying agents that we want to reuse. Now if I take the code from somebody else and put it in the same directory, right, that is not good. That is not a reuse, because someday he might give me a new release and it is confusing that which are the files I need to replace, which are the files that I need to keep it same, right? So you have to organize it properly. So the first step in reuse starts with organizing your code properly. Okay, so how do we organize it? We'll start off from that, and then we'll go deep down into the test bench of UART. We'll start off from the test that we have already established, and then we'll look into how exactly. So here we had looked at the results of that test. Then we'll look at how exactly that test is written, then how it is instancing the environment. In the environment, how the agents are getting instanced, we look into it. How are the interfaces getting passed to them? How is the test being able to initiate the sequences, right, to create the stimulus? Then once a stimulus has been created, how the scoreboards are doing the check, right? How they are doing the checks, and then we look at how the coverage monitor is collecting the functional coverage. And while doing this, all the process, we are going to relate to all the core concepts that we have been already introduced to, right? So each of those core concepts that we have learned, be it like test intent versus the environment separation, how exactly that is happening, how is test rising and dropping the objection, what does it mean when sequence gets started, how the sequence item goes, what exactly is the trial, each of those, right, each of the concepts that we have introduced, how to implement them in one of the possible ways, which will definitely hold up to 60 to 70% for any test bench that you will look at. However complicated, the total number of sequences might be more, but the concept of sequence will remain same. The total number of virtual sequences might be more, but the concept of virtual sequence will remain same. So in this way, for each one of them, we are going to look at in detail the code, and we will follow in phases. We will do the build phase first, do the connect phase, we will do the run phase and report phase. And while each of these phases takes place, what is the role that is being played by test, environment, agents, scoreboard, coverage monitors? So we will look at them. So that is the order in which we will follow, so that it gets intertwined, that UVM concept. How do we do it for UART? We mesh them together, and then we try to gain the overall clarity. Okay, so let's get into with the first part of looking at the UART DUT in the next few slides. We need to connect our UART DUT to Testbench, and in order to do that, we need to understand the interface signals provided by the UART DUT. So let's quickly look at it, and let's just very at high level understand the block diagram view of the UART as well. So UART contains a APB slave logic, and the way it works is typically in a processor you will have multiple hierarchies of buses, as we have seen in the APB overview session, and among them what will happen is that you will either have a AHB or a AXI type of a high speed bus, and then there will be a AXI or AHB to APB type of a master converter, and to that bridge you can connect up to like 16 APB slave devices, and one among them could be UART. That's the overall big picture for you. And so one end you will have the APB slave interface. So this part of the design interface, we also call it as like an application side interface, because it interfaces it to the processor. Okay, so it interfaces to the processor, and processor accesses this design through this slave interface. And another interface that goes towards the processor is the IRQ. Okay, so IRQ also goes towards the processor. Okay, the processor uses IRQ as an interrupt, and whenever an interrupt pin is asserted, it goes ahead and reads a bunch of status registers to figure out what is the source of the interrupt, and then does the processing, right? So from this APB slave interface, it reads and writes this bunch of registers. Okay, that is the main thing. So these registers contain both control as well as status. So we will look into it a little bit more detail as we go through this session, but they contain various control and status register. For example, your divisor register is for baud rate programming. Your line status register tells what is the state of the line. Line control register, you can configure the UART to, let's say, how many bits per data word it needs to use, parity, enable, disable, so on and so forth. Then you have a bunch of FIFO control. So when you want to transmit a word, there is a transmit FIFO, so you can write to the transmit FIFO, and then the design, the actual transmit logic reads it out of that particular FIFO and sends it out. And then you have a RX FIFO, wherein whatever the serial data that we have received, you are converted to parallel word, you write it into this FIFO, and ultimately from this FIFO you read out from the APB slave interface. So when you want to transmit, you write it via this APB slave. There will be a register location, so you write it to TX FIFO, and then that is read by the TX logic present within this UART logic block, and it is sent out on this TXD serial pin. And whatever comes out on the RXD pin, it is converted into a parallel according to what we have configured in the line control register, and then the received data is written into the RX54 and it is mapped to one of the register address in the APB slave logic space, and that is being read from the APB slave interface. That particular address will be read. Whenever the read comes, it will read the word that is present in the RX54. And then there is a FIFO control register through which we can flush these FIFOs or tell the UART to create an interrupt when sort of like the level reaches certain level of occupancy on the RX54 to, for example, to avoid the overflow. You might want to read it as frequently, or like let's say if there is only 4 entries left or only 1 entry left, then you want to read that RX54 quickly so that you want to prevent the overflow from taking place. And then there are a bunch of interrupt control registers, so a bunch of reasons for which interrupts could be generated. There could be error conditions, and there could be like there is no data left to transmit, or the data has been received. So for various conditions the interrupt could be generated, and we can configure what interrupt should be enabled, right? On what conditions should the UART assert the IRQ that goes to the processor. So you can configure it through the interrupt enable register, and when the IRQ is asserted, we can read the reason for that particular interrupt in a prioritized way from the interrupt ID register. And then we also have this modem control interface. We are not going to go very deep into it. Then you have the modem control register and a modem status register. So for all practical purpose, there are a bunch of pins. Whenever they change the states, then the status register gets updated, and through control register you can control on which of the changes do you want to be interrupted, right? So you can do that. So this is the overall sort of the summary of how the UART DUT is looked at. If I may summarize the key points, we have the APB slave interface, and that slave allows us to control these bunch of 9 to 10 registers, and these registers provide the control to the UART logic, and from the UART logic some of the status gets updated to these status registers, and based on that, sometimes if enabled through interrupt enable, then the IRQ it gets asserted, right? So this is the basic idea. So whenever you want to transmit, you write it to TX54, and it will take that particular word according to line control register, format that data word, send it out on TXT, and according to the line control register, it expects the data to come on a RxD pin, like okay, the start bit, data bits, whether the parity bit is enabled or not, stop bit, all whatever that has been configured according to line control register, it expects it on the RxD pin, and once it is received from the RxD, it will write it into the RX54, and then if some interrupts have been configured for receiving the data, then an interrupt can be generated, or the software could be polling this line status register to figure out a data has been received, and whenever the data has been received, it will read one particular register address location, and the data moves in the first order, first out format. So keep reading one after another, automatically gets popped from the FIFO interface, and it is given to the processor interface, right? So this is the overall big picture for you. Don't worry about the modem interface. We are not going to go into the details of that. We will primarily focus on how to transmit, how to receive data from the UART. That is what we will be focusing on in the next few slides. So let's summarize the interface view of UART DUT as a IP in SOC. That's what the picture that we are trying to get to, right? And so we have an APB bus, and what do I mean by facing is whether the ports that we are talking about, do those go out of the chip or do they remain within the chip? That's what we are talking about. So facing, this remains internal because it's an internal. All the APB, AXI, AHP, these are all SOC internal buses, right? So they remain within the SOC. Those interfaces don't become a pins on your entire chip package and go out to the external. That doesn't happen. So it's an internal. And then in any DUT, you have two things. You have a data path, you have a control path, right? So data path is where you actually exchange your data. That is, something is being transmitted, something is being received. That's your data path. And the control path is where you try to read your control and status register. So control and status register is what is the software view or the test bench view of the control logic, right? And through that, you configure your DUT to function in certain way, and once you have configured, you read those status registers either by polling or by interrupt. We'll look at that in a little bit more detail in next 2 slides. Using that, you read the status register to figure out how the DUT is performing. And in this case of UART, both the data path and the control path are controlled through the APB bus only. Like let's say we can have an high speed IP, like let's say USB, in which case what will happen is, for the data path it might use a AXI bus, and for the control path it might use a APB or a AHB bus, right? So that way there can be 2 different buses that are coming into an IP, one for the data path control and other for the register control. And that buses are different because the data path is high speed, it is going to transmit at a very high speed, right? So those are all high speed serial IOs, so they need to pump the data at higher speed, right? But the UART is a low speed serial IO, so it doesn't need a separate data path. So both the data and control for the UART is through APB. So because as we saw, we have the TX54, we have RX54. When you write the data to TX54, it gets serialized and transmitted out according to your line control register, and when the data comes in adhering to the line control register, it gets deserialized and put into the RX54 for you to read from the processor. And whenever you read, that entry gets popped, and then whatever the next entry comes to the head of the FIFO. So that is how the operation happens. And both those transmit, receive, as well as reading the line control register, which is where line status register, which is where you are accessing the control path, or you are programming a line control register to configure it. All that is happening through the APB. So data is accessed through APB, control is accessed through. So both the type of accesses are happening through the APB bus. And then you have the TXT and RXD pins, which are single bit, which are serial pins. One pin is going out and one pin is coming in, and because these are 2 different pins, UART can support full duplex communication, and these 2 pins are external pins. What do I mean by that is that if we put this UART IP inside a sock, then there will be these 2 pins, right? So these 2 pins will definitely come out of the package. So in the package, if somebody gives us the spec of the package, spec of the chip where the UART has been used, and there in the port list we will be able to see these 2 pins. You will see TXT and RXT pins, right? So for example, UART is till, I mean, this whatever the one that we are planning to look at, the 16550 is still being manufactured, for example, by Analog Devices, Texas Instruments. They still manufacture this, right? It is still being used. So you can look it up. So when you look it up, you'll see that the TXT and RXD pins will be present. And then you have the IRQ, which is an interrupt request pin to the CPU. Again, it's an internal pin because it goes to the CPU. So there will be an interrupt controller in SOC. It will go to that interrupt controller, and there it will get aggregated and then sent to the interrupt pin to the CPU, but essentially it remains inside. It doesn't come out as a pin outside your chip package. Okay. Modem control is again an external interface. It's a control interface. These are the interface pins that are used for connecting it to an external modem, which can transmit this data on a different medium. Okay, so that is where this interface comes into picture. And then you have clocks and resets, which again are if it is a part of SOC, then it is internally fed. So your SOC will have internal PLLs to generate different types of clocks, and this clocks and resets will be fed from there. So it will have a centralized clock and a reset handling logic inside the SOC, which caters to all the IPs, and that will feed it to our UART as well. So this is the sort of gives us the overall idea of what are the interface signals and what do we how do we need to configure it. And our primary focus will be on this APB bus, so that we can access the both the data and control, and TXD and RXD, so that we are able to transmit, and a bit of IRQ, right? And clocks and resets, of course, is not much. We will not be worrying too much about the modem interface as a part of this session. We'll just quickly summarize what we discussed from data path and control path point of view, because that's the fundamental on which we are going to build the test bench. So I'm emphasizing this a little bit over here. So CPU interfaces with a UART DOT via APB bus and IRQ. This is the first thing. Then both the control and data path of UART DOT are accessible on the APB bus interface. We talked about it, right? Because like a LSR, which is a line status register, which tells how things are being transmitted or received, is on the APB bus, accessible on the APB bus. Line control register, which allows you to configure how the UART should be formatting the data word that you are programming and should transmit on TXD or receive on RXD, is again all programmable through your APB bus, right? And so those are the control. I'm just giving you one example of status and the control register which are programmed through or accessed through the APB, and I'm telling you that even the data transmission you write to TX54, which is a register sitting on the APB bus. You will see the address of that particular register, and then even when you are receiving from your RX54, that also is a register sitting on the APB bus with a specific address. That's what I mean by the fact that both the data and control path of UART DUT are accessible on the APB bus interface. Okay, compared to, like as I gave you an example, if it were a high speed serial IO type of an IP, then data path could be on a AXI bus to support the high speed serial pins, right? And then the control path still could be on APB or on a AHB, depending on what is the speed of access that particular IP desires in the SOC system. Then control and status registers, as I talked about, are accessed through APB bus. Interrupt is a control path signal indicating various events. So this one point we will see, polling versus interrupt. You might have looked at those concepts, but we will just refresh that. And then the TX data is programmed into UART using the APB bus by writing to an address DR, data register. So there is a common register address that has been mapped called DR, and when you write it, it goes into TX54, and if you read the same address DR, then the data is popped from the RX54. So the received data is read from the UART using the APB bus by reading the address DR. So it's the same address. If you write it, it writes to TX54 and the data gets transmitted. If you read it, it reads it from the TX54. If the data is available, that whatever is the head of the FIFO, the data that is available, that will be read out on the APB bus. And then TXD and RXD are data path pins for transmitting and receiving the data. These are the external pins. These are the actual data path pin that goes out of the chip. Okay, that goes out of the chip, that either send the data or receive the data from the external interface. So we have looked at DUT from its interface point of view, and briefly we have touched based on the programming aspects as well. So from this slide onwards, what we will do is we will go deeper into the software view and formally define it, right? So what exactly is the software view? We will formally define it. Two key things, right? One is registers and second is interface. Those are the software interface. Okay, so first thing, we will define the registers. What are those? We have looked at briefly in the block diagram, but we'll once again go through, and from this point onwards we will get into more specific details, right? So overall is what we looked at for the software view. We looked at it overall. Now we will do it like a specific. So these are the registers, so let's go through them one by one. So we have a RXD register, which we also called it as like a DR or a data registers, and this is, if you see this access, it's a read only, and offset is its address. So what happens is these designs can be mapped at a particular address. So let's say I can map it at in my overall address space, the memory mapped IO address space that we had discussed. In the overall memory mapped address space, let's say I map this particular peripheral at 0xFF00. Let's say that's a 16-bit address that I map it at. Then this offset will be 00, which means that if I want to access a RXD register, I need to perform a read at 0xFF00 because offset is 00. Right? Whereas if I had to perform a read of IER register, then I had to perform a read at 0xFF04. So that's what the offset means. So the overall address is formed by the base address at which this particular IP has been mapped plus the offset that is being specified. Okay, and where does that base address and then the base address based decoding and everything that takes place? That takes place in the bridge. Right, so we had looked at either we could have an AHB to APB bridge, or we can have like a AXI to APB bridge, and that bridge does all this address decoding and mapping it to the peripheral, right? So that is the job of that guy. Now on the bus, when the access comes to this particular peripheral. This peripheral will always see, typically, right, will always see peripheral offset or the address that is coming in on the APB bus to be 00 only. Hex 00 is what it will see. But when the processor issues it, it will issue it to 0 hex FF00, and then the your APB bridge will capture that particular address, and it will have its own mapping mechanisms through which it will figure out that yeah, this belongs to UART, and then it will extract the offset and play it out on the APB bus. That's one of the ways to implement. That is what we will stick to it in this particular example. So depending on the SOC, there could be different ways people could map, whereas the decoding itself could be done by slave. But for the simplicity, let's just stick to with this one. So RxD is at offset 00, width is 8 bits. Although we are considering 32-bit registers, this IP is only going to use the lower 8 bits of those 32-bit, the 32-bit space. So this is the receive FIFO output register. So whenever you read, you are reading the head of the queue, and that particular entry, if it is present, will get popped. And how do you know whether the entry is present or not will be dependent upon the line status register or the interrupt, which we will look at it in the subsequent slides. And then you have a TXT register, which is, if you see, the access type is write only. If you see, the offset is same. Okay, because this is one possibility, that you have a register, and when it is read, it behaves as differently, and then when it is written, it behaves as a different register. That is possible. So this TXT is again at offset 00, width is 8 bits, and it is a write only register. And when you write it, it becomes a transmit FIFO input register. So you write it to this particular address, and it goes into TX FIFO, and thereon the UART logic will pick it up and then transmit it out on the TXT lines. Then you have interrupt enable register, which is at the offset 4, width is 8 bits, can be read or written. Then here we will see that in the future that there are different causes for the interrupt. When the interrupt should be raised, we can enable or disable over here. And then we have the interrupt identification register, which is at the offset 8, width again for all register is 8 bits. It's a read only register, and then whenever you read in a prioritized way, it gives you an ID indicating which of the enabled interrupt event has taken place for which the IRQ was asserted. And then you have the FIFO control register, which is at the offset 8. This is the write only register. It's a control register, and it allows you to flush the FIFO or configure some limits, threshold limits, when the interrupts needs to be generated. Then you have the line control register at the offset C. Again, 8 bits, can be read or written. Line control register is one of the important register for the UART operation, which can help us configure the different properties with which the data word gets formatted and sent or received. And then you have the modem control register at offset hex 10, again read write. And then we have line status register at the offset of hex 14, 8 bits, read only register. So line status register is again an important register for us. We will look into it a little bit more detail. Tells us whether the data is transmitted, received, or do we have some errors in our transmission, reception, not in the transmission, sorry, in the reception if we have some errors. All those type of status information is provided through the line status register. And then we have a modem status register, which tells about the changes in the modem interface. And then we have div1 and div2 together, right? So the one forms the lower 8 bits or the lower byte, another forms the most significant byte or the upper byte. Together it forms the 16-bit baud rate divider value, right? This is the value that is used to derive the baud rate clock, which is eventually used for your transmit and receive data serialization and deserialization. It uses the baud out clock generated out of the baud rate generation logic, which uses this control registers. So these are the various registers, and just sort of make sure that you have gotten a good mental image of this the offset and the different registers, and sort of, like little bit about what type of access types. We will use this for a lot of things, right? So we will use it for building our RAL, and then we will use it while we build the sequences, because we need to read write these registers in order to operate the FIFO. So this is a very important piece of information for building our test bench. So we have looked at like overall registers and where they are placed, what offsets they are placed, and we understood that they are 32-bit addressable, but they are utilizing only the 8 bits, the lower 8 bits. Now within those 8 bits, how it is being divided and what each of those bits represent. For few of the key registers, we'll quickly look at it. This is also a practice as a verification engineer, you are expected to read through like various specification and understand. So this is the specification of 16550 UART. So this is sort of a practice. So how to now read this register? So it's saying is the line control register is one of the important register for the UART, and it says the LCR controls the format of serial characters transmitted and received by the UART. Okay, now let's look at it. So these are the 8 bits. So the leftmost column is indicating the bit positions, and then the second leftmost is indicating what is the type of access. Third column is indicating the description. So bits 1 to 0 access type is read write and defines the number of bits per character. So UART transmits or receives in terms of characters, and those character width can be, if I program 00, it will be 5 bits. If I program 01, it will be 6 bits. If I program 10, it will be 7 bits, and if I program 11, 8 bits. So what it means is, let's say I program it to 5 bits. But we have seen our TXD and RXD registers are 8 bits, right? So I write 8 bit, then if I'm trying to transmit that, then only the lower 5 bits will be transmitted if I have set it to 5 bits. Okay, that is how it works. And then the second bit selects whether the like the number of stop bits that are transmitted. If I say 0, it will transmit 1 stop bit, and if I say 1, then the 2 stop bits are transmitted. So now so depending on what I have set, it will function appropriately. Then I have a third one which says parity enable, 0 for no parity, 1 for parity enabled. Now there can be relation between registers. So now only when the parity is enabled, then the even parity select becomes valid. If there is no parity selected, then the even parity select bit does not have any real significance. So if we have parity selected, then we can choose between even and odd parity. Okay, or we can choose for example this stick parity select. So if there is a 0, then the stick parity is disabled. If we select it as 1, then we will have this some 4th bit which is inverted and transmitted as a parity bit. Okay, so that is how the overall the spec has been defined, and what we have to do is we have to understand this spec and exercise it. Now one of the thing that when I look at this register, what it means to us as a verification engineers is that we need to cross this, right? If you remember the functional coverage, right, we need to cross it. It means that I should have configured for 5 bits, then 1 stop bit, and let's say no parity, and I need to run the full flow, right? And then same thing, 6 bits, let's say no parity, and then no 1 stop bit, and I need to do that. So like this way, whatever the combinations that are possible, let's say with these 5 bits, right, with these 5 bits I will have 5 means here actually up to 6, right? So it's 2 raised to 6. So all the 64 combinations, right? So I need to exercise all the 64 combinations. So I can just take let's say a simple 6-bit vector and keep incrementing it so that I can go through all the combinations. I can randomize it, but since I know that all of these I must be hitting, I can as well take one 6-bit vector and keep incrementing it, go through all the possible combinations, program it into LCR. Note that only programming is not sufficient, so we need to be really transmitting, we need to be really receiving the characters in order to validate the LCR, right? Because LCR's value, if I just program and if I don't transmit or receive anything, then it didn't take effect, right? Just programming is not sufficient. For control registers, you have to program different values and sample it only when the corresponding event where it takes effect has happened. So in this case, when it has been transmitted, you can sample LCR. When it has been received, you can sample LCR, right? So every configuration in transmission has to be exercised. Every configuration while reception has to be exercised, right? So that way you have to have this 6-bit counter, and then you should have exercised both TX and RX with every unique value of that 6 bits. Then only you have completely exercised this LCR register. So this is how you have to approach the specification and think about it. We had looked at LCR, which was a line control register, and this is the line status register. So this is also one of the very important register. And in the poll based mechanism, we look at those two mechanisms. There is a polling mechanism in which you can use a polling mechanism to do the transmission and reception, or you can rely on interrupts to do the transmission and reception of characters. So this line status register is going to be utilized when you do the polling based mechanism. So this has, I think, like all the 8 bits. We'll quickly look at it. So LSR provides the status information from UART, receive and transmit channels. So we have that transmit and receive channels, provides the status information from them. So the 0th bit access types is given. This is all read only because it's a status register. You can't really write to it. And you will see that the 0th bit is a data ready. So 0 indicates no characters in RX54, 1 indicates at least one character in the RX54. So you can keep polling it, and then whenever you see that there is the DR bit is set, you can read it, right? Because you know that there is one character available. And then the bit number 1 indicates there is a overrun error. So if you remember, like even when we were relying on the interrupt, we had some bits that indicate like multiple type of errors that could under. To reset that condition, we had to read the line status register. So when we read the line status register, we'll come to know whether it is a overrun error or a parity error or a framing error, right? So, or a break type of an interrupt. What is the condition that has led to that type of interrupt? Because we had seen that all of these conditions were accumulated together to generate one type of a interrupt code in the IIR. Now, when that happens, you come and read the LSR to figure out which is the specific condition that is leading to that type of an interrupt. And then bit 5 indicates a transmit 54 is empty, and the TX54 empty generates the TX empty interrupt, which means that now you can write more characters to it. You can keep writing up to this becomes full, and then once it has become full, then you wait for the transmit 54 to become empty. And then there is a transmit empty. So here both the transmit shift register and TX54 are empty, right? So as we talked about, there's one extra entry that you can utilize, and if it means 0, the TX54 has at least one character, or TX shift register busy. So this bit is cleared when the character is written into TX54. So when you write it, it becomes clear. So this bit you can utilize for figuring out when to write. And then you have the FIFO error. So it says at least one parity error or a framing error or a break interrupt has been received and stored in the RX54, and this bit is reset on reading the LCR, right? So this is the specification, right? So whatever the specification that has been given, we need to adhere to it and implement the test bench functionality. Okay, there are these two registers which has IIR and IER, which helps us manage the interrupt. So IER enables the interrupt, so all the bits are read write, and then when you write the value 1 to bit 0, for example, it will do the receive data interrupt enable. When you write 1 to the bit 1, it will enable transmit holding register, empty interrupt enable, so on and so forth, right? So for different bits, it will enable that corresponding, enable an interrupt on that corresponding condition. And then so what happens is there are two things. So one, there is that IRQ pin should get asserted to the processor. That is the first thing. And second thing is, when the IRQ gets asserted, now the processor needs to know which condition has led to the interrupt. And the way processor figures it out is by reading this IIR register, and the IIR register reading is what helps us identify the interrupt condition. And then the way IIR register does it is it does the encoding based on like a priority encoder. Okay, so if multiple of these events have taken place, then it will give the the interrupt code based on the priority. And what is the priority that they have indicated over here? So it will give, if it will give 0 1 when there is no interrupt, there is no event that has taken place. If you read IIR and you see a value of hex 1, then there is no interrupt. Now if you see a value of hex 6, it means that there is a receive line status type of an interrupt, which means either there is a parity, overrun, or a framing error, or a break detected. Okay, and then how to reset this particular condition is you have to read the line status register. So in the line status register, you will precisely know what is the condition, that is one among these is what is the code is saying, which exactly the condition that has taken place. You will find it out when you read the line status register, and that will also reset this particular interrupt condition. Okay, and let's say now these two conditions had led to interrupt. Then first time when you read, you'll get this one, and then let's say you follow it up with the line status read. Then next time when you, so the IRQ will still remain asserted, right? And then next time when you read the IIR register, you will be able to see that it is receive data available. Then it will be, you will read the code of hex 4. Okay, and then it says that RX54 trigger level reached. So we will see in the future the FIFO control registers, you can program at what point of the RX54 utilization you would like to be, the processor should be interrupted. That okay, when 16 entries, like let's say when 8 entries are left, should be interrupted, when 4 entries are left, or when 1 entry is left within the RX54. So it can keep accumulating so many, and the processor can continue its job, and when the threshold limit is reached, you want to interrupt the processor so that it can read all of them to prevent the overflow, right? Or depending on how fast the processor can respond to the interrupt, you can decide. If it is very quick, you can keep lower threshold so that a processor can do more work, right? So, or depending on the line speed, so that depends on the application condition, that how do you configure, but it allows you to configure. So next time it will be able to see this, and then so then what it means is the RX54, the processor has to keep reading few entries, and when the number of the entries that become freed up because of the processor reading the entries from the RX54 drops below the threshold that you had configured, then this particular interrupt will get cleared, right? So then you have receive timeout interrupt, then you have transmitter empty type of an interrupt, then you have the modem status interrupt. So this way, in different prioritized way, different types of interrupts can be generated. You can of course read more about all of these in the docs folder of the UART example that is provided with you. We will continue looking at few more of these key registers. So here in this slide we look at transmit and receive channel status. We'll start off with TXT and RXT. So TXT, it's a 8-bit and it's write only. So write to the bottom of the transmit FIFO. So when you write to TXT, then it will write to the bottom of the FIFO, because on the transmit side I keep writing, so whatever you write, it goes at the end, right? And then the other side, it will read it in the order you have written. On the receive side, when you read it from the head of the queue. So read from the top of the receive FIFO when you read the RXT. And these values, as you know, that both of these registers are mapped at the same offset of 0. When we looked at the register address map, we had seen this. Now there is another register called FIFO control register. So FIFO control register is a write only register that allows TX and RX FIFO to be flushed. It can also be used to set the level of RX FIFO threshold, and if you see bit 1, if you set it to 1, the content of RX FIFO will get flushed, and it says but does not affect the reception of any character bit that is in progress when the RX FIFO is flushed. So the way it works is, it has one register in which it keeps accumulating the serial data that is coming in, it is accumulating in that register. So that register won't get affected by this flush. So the total capacity will be whatever your RX FIFO plus 1 extra entry. That extra entry is the register. There it accumulates up to whatever the character width we have specified as per our LCR, and once that has been accumulated, it will write it to the RX54. That's what it means. And then same idea applies to the TX54. So you set the bit number 2, then the TX54 gets flushed but does not affect any in progress transmission. So in progress transmission is read from the queue, from the TX54, put it in your TX register, and then from there you are doing the parallel to serial conversion. So when you flush the TX54, this particular entry doesn't get affected. That's what this line means. And then the last 2 bits indicate the RX54 interrupt threshold we had talked about. If it is 00, it's 1 character. So as soon as 1 character comes into the RX54, it will interrupt the processor. You can interrupt it at 4 characters, 8 characters, or 14 characters, like depending on how much delay sensitive your application is. You can program different number of character threshold, and as and when this threshold is reached, so the interrupt will be generated to the processor. So let's say if I set it to 4, and then by the time processor comes and reads, let's say we have accumulated 6 characters, then as processor reads 1, then it becomes 5, the interrupt won't drop. Okay, then it reads 1 more, right, and then it becomes 4, the still interrupt won't. 1 more it reads, it becomes 3. When it becomes less than the threshold, then only the interrupt will drop. Till that, the interrupt will stay asserted for the processor to read the number of entries from the RX54 to make it drop below the threshold. So we have looked at various individual registers. Now what we will do is we will look at what are the 2 ways in which we can use these registers and accomplish our primary functionality. And always remember this in a design, when you are verifying a particular IP, find out what is the primary functionality. For example, for UART, it's always transmitting and receiving the characters, right? So that is the primary functionality. What that means is, now if I'm implementing a functional coverage, or if I'm implementing any scenarios, right, like just programming LCR is meaningless. I have to program LCR and do some transmission and reception, because that is when that LCR value that I have programmed gets used. So what you need to understand is the if in the verification solar system, your primary functionality is the sun. The rest everything, it might be different control registers, status registers, different feature interaction, everything else happens in the context of your primary functionality. Without that, if you do something, it's not much meaningful. Okay, even if you are doing low power verification, you need to do some data traffic, get into low power entry, exit, then again do data traffic. Okay, your primary functionality must be present in every test that you do. That is only when it is meaningful. So now in order to, so what is the primary functionality for the UART? It is nothing but transmission and reception of the characters, right? And there are 2 ways in which we can accomplish this goal. We can do polling and interrupt. So why do we need why do we need a method at all? So what happens, we have a limited space in the TX54 or RX54, right? So if I keep writing, and let's say that my processor bus side speed is much higher, and I have programmed a very low baud rate, then my TX54 can quickly become full. Then how do I know when can I come back and write it, right? So that is a question. Or on the receive side, when do I know that there is a character available that a processor can read? So to know these, there are 2 ways in which a processor can know about these things. One is it can do polling. So in the polling, what happens is it keeps reading the line status register with some delay. So you put some delay and keep reading it, and whenever it shows that data is available with that bit DR, then you read the RX54, and then if you had written many bytes and you had found that every time after writing you read this line status register and look at it, that if the FIFO there is no more space left, the FIFO empty is not showing you any space, then you have to stop writing, right? And then once you have stopped it, then you have to again keep polling for that, keep looking for that periodically to see that if there is now any more space that has become available, then only you can write into it, right? You can do this way, right? So this way you can figure out when there is a space in the TX54, you write it, and when there's a character available in the RX54, you read it. Certain disadvantages to these methods are that loads the CPU and blocks the other. Loads means CPU has to do that job of polling, right? So it's consuming CPU cycles. and it, like, if there is any other task that the CPU could have done, it's blocking it, and the CPU has become busy polling this particular register. Polling means it is reading, continuously reading. We will see in the waveforms what this means. When you look at the physical waveforms become more clear. We look at the, like, periodically you will see a read pulse coming to, let's say, LSR register when you do the polling. But then the other thing that can happen is, depending on the delay, right, that if the delay between reading the register is too high, then a character might have come and it could have caused overflow in your RX buffer, right? So it has come and it has been overrun. That can happen if the delay is too long. Now looking at these disadvantages, one might think, why do we need the polling at all? But it's not correct to think like that. Polling is also used in certain applications. If some application has tuned it properly, where it's very performance sensitive type of application, then they tune the polling such that if every time I poll, if I hit one condition which I am looking for next, that's very optimum compared to doing the interrupt. Now in the interrupt type of a thing, what you do is you enable relevant type of interrupts to get notified about the condition that you care about, right? Like I can enable and receive data interrupt, and then whenever a character has been received, I have programmed the corresponding threshold, and based on the threshold I get notified, and then on the interrupt I'll go and read the RX54 register, right? And then you have the like, let's say you start writing it into TX54 register, and let's say it becomes full, then you would have enabled the TX54 empty interrupt, okay? And then whenever the empty interrupt comes, you again start writing into the FIFO. So in this way, when you use the interrupt method, then your CPU cycles aren't getting wasted, and then there is no fear of data loss, because anytime a character becomes available, it will give an interrupt and you can come back and read immediately. But as we talked about, there is always like a ISR overhead in the software. So depending on the application, both the methods are appropriately utilized. So we have looked at the different views of the DUT. We have looked at the interface view. We have looked at various, look at the software view by looking at various registers and what are the fields that are present. And now we will look at like what are the different tests that are included in this particular test bench, and which is the test that we are going to do a deep dive. So we have, like, typically in any such IPs, you will have 3 to 4 categories of tests. So you'll have register access tests, you'll have normal operation tests, you'll have error injection tests, and typically a low power test. So remember that these 4 categories will be generally present in most of the IPs. And why I'm emphasizing it is that given any IP, if somebody were to ask you to create a test plan, you need to think in terms of these 4 major categories. That you need to have some tests for register access, some tests for normal operation, some tests for error injection, and some tests for the low power. So in the register access test, we have this UART test.svh. It does read, write, and read of all the registers, and generally this type of tests are very useful. So on power on, you read all the register values and check if they are matching the power on reset value. So if you remember in the previous register specifications that we saw, at the bottom they will mention the reset value. In the specification, they will mention below each of the register description, they will mention power on reset value. So immediately after the DUT powers on, without programming anything, you read those register and check if it is matching the power on reset value, and then you do write all the registers with some random value, and then what you do is you read them back and check whether only the right fields have gotten updated. So that is a type of test. That is a type of check that this type of test can do. And then we have bunch of normal operation tests, and the theme is sort of same, you will be able to see. So we have word format poll and word format interrupt. So what it does is it randomizes the word format. Word format is our that LCR register, where number of bits per character, whether the stop bit is enabled, and then whether the parity is enabled. With those configuration bits being randomized, you transmit and receive, and then the when to transmit, when to receive. In the polling case, you rely on polling, and in the interrupt case, you rely on the interrupt, right? So based on the interrupt, you do the transmission and reception. And then you have baud rate test, where you program the different div value and check whether the baud clock that is generated is as per the div value that you have programmed. Ideally, this test also should be doing additional data transmission and reception. Since this is the sample test bench, it is just checking the baud out clock. And then you have a couple of other normal operation tests. The theme is same. it will do the changes in the modem interface pins, and then check that those changes have taken place either by polling or by relying on the interrupt. You enable appropriate interrupts, and then based on the interrupt you read the changes and check what is the values that they are reflecting. And then you have this another interesting case, which is the error injection case. It's called RX error interrupt test. So here you do the concurrent transmission and reception. Transmission you do it based on the polling, okay. Reception you do based on the interrupt. And reception, whenever we talk about the direction, we generally talk from the DUT's point of view. So whatever is DUT is receiving, the UART agent will inject some errors in it, okay, because only the test bench can inject the error. If the design injects any error, those will be caught by the test bench as errors, okay. But agent or the test bench can introduce errors, and for those errors the DUT should detect them. Like for example, if I inject a parity error, the DUT should be able to detect and report it. That is a part of logic that we are checking when we inject error on the receive side of the DUT, okay. From the test bench you inject error on the receive side of the DUT. So these are the bunch of tests, and what we will be doing is, as a part of this bootstrapping session, we will be going deep into this word format poll test. Rest of them it's open for exploration. The code will be available. You can look it up and try to understand this on your own, and if you have any questions, of course you can share it. We had selected this word format poll test. So the way to run it is, I'm just showing it with the QuestaSim command line, but the same concept can be applied to any of the simulators. So we say simulator, and the key parts to notice are, like, we have to pass this UVM test name equal to word format poll test, okay. So we will be seeing in the further session that how this translates further, and then we will be specifying the UVM verbosity is equal to UVM debug, okay. So what these two mean, we will look at it in the some of the further slides, but this is what the key thing is, that you say simulator UVM test name equal to something, and then UVM verbosity equal to UVM debug. Ignore the rest of the arguments. You are just specifying the log name, and ignore the rest of the arguments. So focus on this. So you say simulator UVM test name equal to word format poll test, and then you pass the UVM verbosity is equal to UVM debug to enable the maximum number of messages to come out of the test bench, okay. And when you do this, the log file would look something like this. So this log file snippet I have divided into three sort of categories. First is the simulation log snippet at the start. Typically at the start you print the topology of your test bench, and you will be able to see that you have UVM desktop, and then you have environment, and then you have bunch of agents, and then within the agents there are different components that are present, right. So we will look at it in more detail, but just remember that any typical file consists of these three set of information. This is what you need to remember, so that when you start doing the real debug, this will come in handy, that in your mind keep this information, that it will consist of three categories. You will come to know the configuration, right, and what configuration are we running. You remember we had structural configuration and functional configuration. So this is like your structural configuration of your test bench. The functional configuration, eventually each of the config objects will be printed. So using those two, you will come to know how the test bench has been configured. So first step in the log to find out is what is the configuration in which we are running the test, and then you move to the next step, wherein the actual test will start executing and it will start generating the traffic. So you will see repetitive messages being printed by different components. The generator will print some information, then your agents will print it, your driver will print it, monitors will print it, scoreboards will print it. So different components will log the information at different points of time, and with UVM all the logging format gets standardized. How it is getting standardized, what is the format of it, we will be looking at it when we go deeper and deeper. But for now, understand that if we had put just the dollar display, then we wouldn't have a control saying that, okay, from which file is it coming, which line is it coming, what is the ID source for this particular message, all that, and then the actual timestamp, the message, right? So there are various things that we want to keep the standardized formatting. That is very hard because one component owner might choose one style, another component owner might choose another style, and we don't have any control. But when we do it in the UVM, you have the control, and this is a very important part because then anybody can look at the simulation log and understand and sort of extract and process the information. So that is the second part. So you looked at first the configuration information, and second part is that the test has run and the messages from different components have been logged in a standard format. And then I have not shown the entire log file. There will be lot many more number of lines, and then towards the end it will indicate, like, the summary of how the test has progressed. And very important point will be, like, how many if there are number of errors or warnings, number of info messages. It will show all those statistics. Those will be very useful while you are doing the debug. Even sometimes warnings can give you hint, so you should definitely look at this information that gets printed towards the end. So in summary, your log file, first part configuration, second part various traffic in a standardized format, third part is the statistics that is printed by UVM as to what is the type of number of messages that have come in. At the end, even your components can provide some sort of statistics that we will look at it. Before the UVM prints its statistics, your Testbench components can also print some of the statistics that can be done in the report phase. So as a part of session towards the end, we will see how the test and the scoreboard is going to provide some statistics information. What happens is, when you run the constrained random stimulus, you generally don't know like what exactly the stimulus that has been generated by test, right? So based on the seed, it can generate different complex scenarios. However, here we have relatively simple test bench, and we have relatively simpler scenarios, but the method that we are following is applicable for any test bench, right? That is a point that you need to keep in mind. The method that we are following, we are not following the simplified methods just because it is a simpler test bench. We are following standard methods which you can employ for any of the complex test benches as well. So what you do, the log file may contain like 50,000, sometimes up to 1 lakh lines of various information that is dumped by different components. So obviously you can't read the log file end to end. You generally read some configuration information, and then for the traffic, right, the configuration information might be in some tabular format, so you might still read it line by line to understand how it has been configured. But once you have understood that, the next of it, traffic, you generally run your Linux commands. You generally use this grep command. So grep is a very useful and a very powerful command, so you should practice this more. So here what we are saying, let's say the first thing, we know that both our data path and control path coming towards the UART are all controlled by APB bus, and we are reading or writing some set of registers to stimulate our DUT. That is the main thing that we are doing from the processor side. So how do I find that out? You initially once look at it, read the various messages one time just to understand what is coming in, then to extract some type of information, you grep it. So first time while reading, I would have looked at reg model some of these messages, and after I figured out that this is a useful message, I'll come in and I'll say grep rote register. So rote register is part of that string line that I figured it out from the log file, and then used few words, unique words from that particular line to grep out all similar lines from the log file. And because I need to know what has been programmed into the UART, that is the first step I need to know, right? So I have not looked at the test code. Okay, I don't know anything about the source code. I just want to understand what has happened in the test scenario. The way you do it is look at few lines, and if you see a lot of repetition of them, you know that that's generating some stimulus, and then you know that you need to have some sense of what the DUT is doing. So here I want to see which of the registers have been written. So I am seeing that it wrote to the LCR00. Yeah, this gives me some idea because I know how to decode this, right? Because we already looked at the LCR format and I can decode it. And then it has written something to FCR. Yeah, this also I can decode. Div1 and Div2 baud rate generation has been programmed. And then it is wrote register to TXD. It has written to. And we know that when we write to TXD, it is writing it for the transmission. So it is configuring in the first block, right? Because these are all control registers, it has configured it. And in the second, it is trying to write the TXD. right? And it is that whatever you write to txt goes to txt4 and then gets transmitted further. So this much I understood by looking at, by grabbing this information, that it has trying to transmit two characters, right? And sometimes, like if the total number are too huge, you might want to just check the total counts. You can use this pipe and wc minus l to count, and this also is very useful. So not only you have to grep it, you can combine it with wc, and you can do the sort, you can do the unique command. So all those help you get a sense of what has happened in the test. So we looked at the register rights, and based on that we could understand how it has been configured, and that we can understand that like two characters have been transmitted. So now similarly what you will do is you will look at the read part, right? So I grabbed for read register on this word format poll.log, and if I check, there are about 39 reads. So now that will give you some sense, right? So you were expecting that we are doing the poll test, right? So once we know that we are going to be reading this LSR register periodically, right? So that I already have that sort of an idea about DUT. That is very important. The software view of the DUT should be clear, otherwise debugging will become very hard. So I will now grep for this LSR and count it. Then I see that okay, 36 out of 39 reads have been to LSR, and that is just a polling, right? So I am doing the polling to see what is happening. Now what I will do, I will say grep minus v. Minus v will exclude LSR string from that to see what else has been read. So I see that okay, LCR has been read, and then it has read the register RxD, right? So here we can see that it has read the RxD twice. So what that means is that two characters have been received, right? Because whenever we read the RxD, we pop the data from the RX50, right? So we have transmitted two characters and we have received two characters. This is the information that we could figure out without really looking at the test, right? So we just looked at the log files, we understood few statements, we grabbed few information, we applied what we know about DUT, and based on that we understood what the test has done. This is the way that, this is the approach that you need to learn to follow, because sometimes tests can be very complicated and there can be various knobs that are passed. So not all the time. So you need to do it in combination, that you sometimes you can read part of test, but you should become comfortable reading test. That comfort is understandable, that you can definitely gain that. But the second part that I'm talking about, that like jumping into this unknown log file and being able to identify few information, being able to grep that, and being able to decipher or correlate this information back to what you have read in the test is going to be a very critical skill for you to do the debugging. And for that you need to gain a bit of proficiency with the Linux command and the understanding of how the DUT works and how the logging is done. And the standardized logging of course gives you much more control because the formats and all that will be very common, and hence the string to pick for grepping will become much more simpler comparatively, right? If everybody had done to their own wish, then it would have been relatively much more harder, but relatively it becomes simpler. So we saw that LCR was programmed with the value 0, right? So we saw that in the, when we extracted the write to registers. So the what you then need to do is you should then go back to the register definition as per the documentation, and then map that value to different bits and try to make a sense of how exactly it has been configured. So in this case, when you write 0, then we are saying that it's 5 bits per character, because 0 in the bit positions 1:0 means 5 bit, and then it means, like for example, even the second bit is value 0, which means one stop bit, and then third says that it is no parity, right? And then rest of them are again all 0, right? So stick parity is disabled and break is disabled, all of them are disabled. So what we are essentially saying is that we have 5 bits per character, one stop bit and no parity. That is what we are expecting to see on the lines. And then we saw that txd was written twice. So txd was once written at the timestamp 87 and it was written with the value 5d. So if I decode that 5d, it will become this 0101, that would be the higher nibble, and the lower nibble will be 1101 for D. And then generally the transmission will start from the LSB of this particular byte. So on the line, when we see, on the serial line when we see, it will start from this LSB, so it will be 1011 and 1, because we are only going to be transmitting the 5 bits, right? Starting from the LSB, this is what we are expecting to see. And then for the TXD, we wrote one more value, E9. If I expand it, it becomes 1110_1001, and then again the transmission on the line will start from the LSB, so it is 1001_0. This is what we will be seeing on the line. On the TXT, if we look at it, these are the like 1011_1 and 1001_0 is what we will be looking at. Similarly, for the read at timestamp 601, we saw that hex 19 has been received. When we convert it to binary, it looks something like this. So on the line, we will be seeing again 1001_1 being received for the first character, and second character was 1B. So this is the binary representation. Again, starting from the LSB, we will be seeing 1101 and _1. This is the order in which we will see the data on the line. So this way you have to look at the log files, extract some information, and then look at how the DUT has been configured. So this LCR is nothing but our functional configuration. We don't have much of a structural configuration here because we are not varying the structural elements. We just have one UART port, so we don't have much to configure structurally, but functionally the functional configuration registers are LCR, for example. So LCR we have configured in this particular way, and that information you should be able to decode it and utilize it in a way that I explained. Now next step, we will look at it further in terms of on the lines how exactly it is behaving. We are trying to demonstrate a debug flow. However, this test has not failed, but the principles that I am showing you is what you need to be following even in your real life debug cases, right? So the first step, you should not directly jump into the waveforms. That's the general practice all of us we have when we start off doing the verification, because we would have done some small example simulations, and in those cases we have generally looked at the waveforms. So there is a tendency that the first step itself jump into the waveforms. You should not do that. Not especially for the test that has run for a longer duration of time. If it has immediately failed immediately after reset or a first transaction, then that is fine. There might be a very basic issue, so you can directly jump into waveform and look at it. But if a test has run for a length and it has generated a lot of traffic, you should not directly be jumping into the waveforms. You have to remember that first step is always you have to force yourself to look at the log file and extract the stimulus. Why I am saying that is, even if I read the test, I will be seeing transaction.randomize. When I look at transaction.randomize, I cannot figure out like what random values have been generated. To understand what random values have been generated, I have to look into the log files, and since there will be so many statements, similar type of repeating statements, because I'm repeatedly generating multiple sequence items, I will see multiple prints, right? So I cannot understand I cannot sequentially read them. So you have to figure out initially, establish which are the important messages, and then once you have established the important messages, maybe you can make a note of it in your own text file, and then every time then later on when you have to read the log file, reading the log file is not sequentially reading the log file. You have to grep out the traffic information from the simulation log file, okay, and you have to do the analysis on that. And only after doing those analysis, when you have localized the region to a specific point, some 2 timestamps you have localized, then you come to the waveform. So imagine we have done that process. We have looked at a simulation log file, broad structure we understood, then I identified few important statements from the log file, we grepped them. Now we have come to the waveform to see whether what we have seen in the log file is sort of matching with the waveform. That is our current intent. But in debugging, you will be looking at you would be the error message would be saying, okay, I was expecting this byte, but I have gotten this byte. Then what you will do is from that point you will first spot it in the waveform and backtrace to a point where the expected value, like the actual value, whatever the value that has come, at what point it has deviated from what is the expected value. That is how you do it. So let's understand this waveform. So in this waveform, we have multiple sections. So we'll first start off on the transmit path, and then we'll look at the receive path. And what we have done over here. So if you look at it, this is the write register, right? And then here, for example, if you see, we have written our LCR register, we have written our div register. We can add more register writes, but I am just showing few snippets that few key registers have been written. Each of these pulse is a write. Okay, I have not shown the clock because it's very dense, so but you can imagine that this is one clock pulse. And then I see that my TXT register has been written twice, and I know that once the TXT is written, it goes into the TX54 and the UART starts transmitting the data on the TXT serial line. Okay, so then I come to TXT serial line over here, and this is my TXT serial line. And what I am looking at over here is at the top I am seeing that I have a state machine, right? So in the design there is a state machine for transmitting, which actually does the the character formatting. And how it does is it will first go through the start bit, and then it will transmit bit 0, 1, 2, 3 and 4. It is transmitting only 5 bits because we have configured LCR to transmit only 5-bit word, right? 5-bit character. And then it is transmitting only one stop bit because that's what we have configured. We have not configured for any parity. Okay, and we had noted that at timestamp 87 we had written 5D. So from here, since I cannot show you the actual value, I am just showing you that at 5D is what we had written, and then that means this particular value. And on the line we should be able to see 10111, like 10 and followed by 111. So if you look at it over here on the start, the line has gone low, and when the bit 0 is 1 corresponding to this, it has gone to 0, and then we have 3 ones, right? And then we have the stop bit, which is also 1. So we have bit 2 is 1, bit 3 is 1, bit 4 is 1, and then the stop is 1, right? And the same thing, it has transmitted the next character. So line goes low during the start, and then it will transmit 1001 followed by 0. So it is 1001, and then the bit 4 is 0, and then the stop bit again goes 1, right? And so this is how the transmit is working. So I have written these two characters, and those two characters have been transmitted on the line, and those whatever is being transmitted is matching whatever the data that I have written to TXT. So I am able to now correlate from the log to the waveforms. Okay, this is a very important step, that I should be able to correlate my source code, my specification, my log file, and the waveforms. Okay, I'm going to repeat this once again because it's a very important. The overall process of debugging will involve correlating specification, correlating to source code, then correlating to the log files, and then correlating to the waveform. So you should be able to correlate all 4 of them. We saw LCR, how it is programmed, and we correlated that in the log file. From the log file we extracted, correlated that to the specification, brought it to waveform, and we are able to confirm that it is doing in the same way. So this is a process that you do while you are doing the debugs of the failure. Okay, now let's quickly look at how do you do it on the RX as well. Not very different. So on the RX path, what happens is the data will keep coming serially. So this is the data that we had read at 601 that comes at here, somewhere here. Okay, this is the point. This is a read to the RxD where we are getting it. We will go into the register read. Just hold that thought for a while. So first look at the serial line, because first we have to receive the data in order for the processor to read it. So again, on the receive side also we have a state machine which takes us through like a start, and then bit 0, bit 1, bit 2, bit 3, so on and so forth. It starts from the idle here. So we have the start, and once the start is detected from idle, it moves to the bit 0, and we will be able to see this data coming in serially. That will be your 1 0 0 1, right? And then we have one more 1, and then the stop bit, right? So and that will be completing this particular pattern, right? So 1 0 0, and then we have 2 1s, right? 2 1s, and then we have the stop bit, right? So same thing. And then the second 5-bit character that is coming in is 1 1 0 1 and 1, right? So if we look at it over here, after the start bit it will be 1 1 0, then 1 1, and then the stop bit will be 1. So if you look at it over here, once this entire character has been received after the stop 1, when the line goes back to idle, is when the your UART receive logic will write it into the FIFO. And if you see here, so you remember we were polling the LSR register, and we had seen about like 36 reads to LSR register, and these pulses that you see over here are all polling, right? This is the polling. So we keep on polling, and once the state machine has come to idle over here after receiving one character, the polling becomes successful. It will indicate that the data ready will come, and once the data ready has come, then we have read the RxD register, and when we read that particular RxD register, we would have found this value 19 in it. Okay, same thing, once this guy completes, the second character reception completes, again the polling becomes successful, and once the polling becomes successful, we do the read to the RxD, and then we get the next data character, that is 1B. Okay, so this gives you a big picture of this word format poll test, how it is transmitting two characters and how it is receiving two characters. Okay, and in the next set of sections, what we are going to do is we will look at the UVM test bench and map the UVM test environment sequences, how all of it works in order to be able to do this, right? How exactly do we poll, how exactly do we read the register, everything, right? And how exactly, we have not talked about checking, for example, coverage, for example, all those aspects, how to generate stimulus, how to generate the how to do the check and self-checking, and how to do the functional coverage. All of it we will look at, keeping this test as the anchor point, right? So we'll use this test as the anchor point, and then around it we look at the flow end to end, and we look at the phasing. Basically we will stitch everything together now for the UVM test bench using this test as an anchor point. That will be the next section. This concludes the part 1 of bootstrapping, wherein what we have established so far is we have understood about DUT. Okay, so we had figured it out that we need to know about DUT from 3 points of view. What is the interface, so that we can connect the DUT to our test bench. Second, what is the software view of it, so that we can program the DUT. And we had understood for the UART DUT, our both the data path as well as control path are all accessible through the APB. That's the part we had figured it out. And then the third was the protocol view. So protocol view, we have only looked at it briefly. UART protocol, we have not covered it exhaustively, but briefly we have explained enough to make sense of the test bench exploration that we intend to do. Okay, at the very high level, we have indicated that it is just, you know, parallel to serial conversion on the transmit path and a serial to parallel conversion on the reception side, and then we have a bunch of FIFOs, and those FIFOs are interfaced using the register block. So we have understood that. In the software view, we have gone through the details of all the key registers, how they function, all that details we have specified, and then we have put together a flow. We indicated that we can do polling as well as an interrupt based flow, and then we looked at what are the test cases that are present in this particular test bench, and then we selected one of the tests, that word format poll test, and the intent of that test was to randomly program a LCR value and then do 2 character transmission and 2 character reception. And what we did was we took it, looked at the command line, looked at the simulation log file. From the simulation log file, we understood what are the 3 sections: the configuration, traffic, and then the end of test statistics. And then in the traffic part, we identified the key display statements, and we grabbed those key display statements to understand, correlate to what we were expecting, or what exactly the test has done. So we understood the stimulus part, and then we went through the exercise of correlating that stimulus in the waveform to make sure that the view becomes complete. So we looked at the we understood the spec, then we extracted the information, mapped it to the spec, then looked into the waveform to make sure that it is spec compliant. This is the process that you will repeat again and again when you do the debug process. But this now sets the foundation. With this understanding, now what we will do is, next step, we will go into the how to build the test bench, okay, for the UVM test bench, and that will be the part 2, and that will give you the clarity of whatever you saw in the simulation log file, how exactly test did that. Okay, so let's look at that in the part 2, and thank you for listening.